Right, class. Let's continue from where we left last time. Once again, we're looking at basics of organic chemistry molecules. And though they may appear basic, but you require this knowledge in the in the understanding of heterocyclic uh, molecules. Uh, Now, in general, this is how you show something like a linear structure. This one has got let's say like one, two, three, four, five carbon atoms. This is what you're just going to illustrate. But what you just need to know is that in reality, the bonds exist like a zigzag, like I've shown, for example, like in this structure here. It is not linear. It is. Let me just put it correctly. It's like a zigzag, yeah. Uh, so this is what you're going to get, something like this zigzag, which you're going to show in the shorthand form as this bond line structure, yeah? Zigzag, one, two, one, two, three, four, five. By now, I think you just know. When you're just going to see at the end, you know that it's carbon with three hydrogens. When you're just not going to see anything there, like two bonds, then you're going to show it's implying two hydrogens. I think now it's clear now. This two hydrogens, three hydrogens. Yeah. Now, for uh, for a cyclic ring, it may look linear, but okay. I've just tried to show here. Um, uh, I could put atoms of the same size, but I've just put different colors here to illustrate. Oh, okay. Let me just try to to shift this one. Excuse me. There's a point I'm just trying to drive at. Let me get it correctly. Okay, good. Yeah. So can you see this structure being shown here? So there are some hydrogens which are facing at the top. So these are called axial hydrogens. They are pointing at the top here, and the ones which are shown in blue, they are on the like almost the horizontal axis, called the equatorial. Yeah. So even though this one is it's like it's being shown as a hexagon, if I'm just going to show it near the board here, it may not be seen very well here, but it's actually a chair structure. Yeah, there is this point which is at the bottom, and this at the top and the bottom here. But I think to really show this one very well, I've got another illustration of the same cyclohexane using a different model, and I think it may be able to really show well. It's just the same uh, cyclohexane, yeah? Can you see it's a six-member ring? So in this case, the white atoms are the white ones are equatorial. Now the red ones are axial. I think this would be the best one to really show the chair form. These are the top and these are the bottom. Can you see the chair? This is how the chair looks like. Yeah. Let, let me show it in this form here. So this the where you sit. This the flat and this the bottom one. Can you see this how the chair form? Now this is what I'm going to show it in this form here, and I'm saying it is in equilibrium of in this other form here. Please note this. If I'm going to change to this other form of the same thing, all the atoms which were initially axial will change to be equatorial, and the ones which are equatorial will change to be axial. Can you see this form here? These are the top and these are the bottom. So what I want to do, uh, please note here, in this case, the red ones are axial. So let me change it to this other form here. So this other form here, I want to put it at the top, and this other one I want to put at the bottom here. Can you see what I've done? The red ones, which were initially axial, they are now equatorial. Can 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 you see this form of the chair? Let me, let me show it here, like in this form here. Let me just try to put it in this form in the camera here. So these are the top, this is horizontal, and this is at the bottom, yeah. And then this is the other form of the chair. Can you see here? Uh, these are the top and these are the bottom, and these are sorry, excuse me. it's coming out. So this the form of this other chair, and then if I flip it, this how it change. So this is the chair form. Uh, Forget about the boat. Yeah, this is the boat. Can you see this? What's called as the boat? You've got two sides at the bottom, but it's not as stable as the chair form. Okay, good. All right. So I think I'm moving a little bit quickly because you've encountered this ones in the earlier years, but it's good to really show you this because you're going to make use of this structure. So I'm just going to to pause a bit to be able to make the molecular models to show like the aromatic system. Now in this case, what you've seen, like in this case, before I really pause, if I have the linear, is I mean if it is saturated like for the cyclohexane here, it's not flat. It is not flat on the plane. Yeah, and the bond angles are 109.5. What you're going to see is that if it will be flat on the plane, then the bond angles are going to be 120 degrees. Yeah, in that if it will be flat, then there won't be this top bottom. Yeah, these things which are going to see top bottom. This thing is not flat. Uh, but want to see how we can make a structure like for benzene, and then what we're going to see is that what's going to happen if we're going to introduce an atom here. Uh, but the thing is, what you're just going to see is that uh, if you're going to have a six-member ring, then the bond angles are not going to be strained. They will be relaxed. The bond angles are going to be something like 120 degrees if it will be flat. But if it will be linear like this one, all the bond angles are going to be 109.5. Yeah, it's going to be there won't be any strain in the structure. But what you're going to see is that later, if I'm going to have like for the five-member ring, like in this case, whereby you're introducing an atom here to make this structure, which you're going to call pyrrole, you're going to see that the structure will, the bond angles here are going to be less than the ideal 120 degrees, and therefore that will lead to less aromatic character. If there will be strain in the molecule, then the aromatic character will be lower. And I think this thing is covered in the notes. So I'm going to pause the video shortly, and then I'll go to illustrating like for the benzene, and then you're going to see this molecule which you're going to call pyridine. You're going to see how uh, for example, if I've got a lone pair here, how are you going to show it uh, on a 3D structure? Yeah. So I'm just going to pause a bit, and then I'll just try to see how I can show this structure. Okay. I hope you are following up this illustration. So I'm going to pause. Yeah. All right, class. Okay. Let's continue. All right. So here, what I've just tried to do is to create something like a benzene in which there are uh, there are three pi bonds. Yeah, like just put on different colors. There's the purple here. So this is one pi bond. There's a second pi bond, and there's the third pi bond. Yeah, which is being shown in gray. There's the other one which is shown in brown. Yeah. So there are three pi bonds. What can you see here is that is that is that this structure is now flat. It's now flat, and then the p orbitals, they are okay. It being flat, you can say it's along the x or the x and y axis. So the p orbitals are along the the vertical plane, which you are going to call the z axis. So the hydrogens are coming out here, and uh, so the thing is, as long as this structure is, I mean, these p orbitals are flat, then the electron density can flow around. So if this structure is flat and it's got for aromaticity, you need to have this number. The pi orbitals, the p orbitals has to be 2n plus 2, where n is equals to 1, 2, and the rest. Yeah. So when n is 1, you're going to get that you're going to have uh, uh, six p orbitals. Yeah, are you okay? Six p orbitals. Okay, so in this case, um, this structure is aromatic. So what I want to do is that uh, for simplicity case, I just want to introduce an atomere. Let me say the atomere is is yeah, is nitrogen here. Um, what I'm just going to do is that uh, okay, there are places whereby I can insert uh, uh, a lone pair. So what I'm going to do is that let me just try to use one of the lone pairs which I had earlier. I think let me just try to see how best I can get such a structure. Okay, let me say I want to introduce a lone pair at in one of these atoms here, and then probably put uh, okay, sorry, not that one. Let me put it correctly. Excuse me. Okay, so like in this case, I've got this structure which I'm going to call pyridine. Okay, pardon me for the big orbital because I had a small number of these illustrations for these orbitals. Yeah. So the thing is, if I've got a lone pair on an atom which is participating in aromaticity, then the next uh, uh, p orbital. What I'm saying is this. Let me say this lone pair is in a p orbital. Are you okay? Now I think it's now clear. So I can illustrate here to show a p orbital. So this p orbital will have to be perpendicular to the plane of the aromaticity here. So that in this case, can you see here? If I'm going to illustrate here, okay, is it clear? Okay, let me just show it well. Yeah, excuse me, it's flat. Yeah, okay. So you've got your aromatic ring which is at the top and the bottom, which it's yeah, the structure is flat. But now if you are going to have your lone pair, then the lone pair is going to be 90 degrees to the plane of the aromaticity. So an atom in the ring uh, can have a lone pair and still the structure will be aromatic because this lone pair does not interfere with the aromaticity. So this lone pair can bond. For example, I can say, um, excuse me, it can bond with a hydrogen like in this case, and this bond is going to be 90 degrees to the plane of the aromaticity here. So it's not going to interfere here. Is that clear? So you're going to say this structure, which has got a nitrogen atom and uh, and, and it has three pi bonds. So this structure is still aromatic. The the aromatic system is along the z-axis, and in this case, the lone pair is along either the x or the y-axis, whichever one you're going to see. So perpendicular p orbitals do not interact. Is that okay? Perpendicular p orbitals do not do not interact. Um, so if I'm going to so in this case, the bond angles are going to be 120 degrees. Yeah, the bond angles are going to be 120 degrees. But if I'm going to put a 5-member ring instead of a 6-member ring, then the bond angles are going to be less than the 120 degrees. So the structure will be strained. If it will be strained, then you're going to say there will be less aromatic character. There will be less aromatic character. So for 5-membered structures, the then there will be less aromatic character. In this case, you're going to see a structure like like which are going to call pyrrole, like where there's the nitrogen, where there's the oxygen, you're going to call the structure furan, and where there's the sulfur, then you're going to call it thiophene. Yeah, okay. You're going to see they're going to have a less aromatic character than uh, than the six-membered ring, which in this case we're going to call pyridine. Yeah, but all those things they are at the beginning of the module, uh, uh, which as you look, you'll see the patterns for aromaticity. Okay, so I think I'm just going to stop there. Then I think in a short while we're going to see how uh, yeah, the orbitals are going to help us. Uh, uh, okay, what you're going to do first, it will be to show how a reaction you're going to show with things such as Kali arrows, and then you're going to show how using the molecular, how using the orbitals, it may be a bit complicated, but that will, if you're going to use it in conjunction with Kali arrows, then I think everything is going to make sense. So I really hope you've really enjoyed this session. Once again, these are short sessions. Like now, this one is close to 17 minutes. Yeah, close to 20 minutes with short videos in which you can pause, you can rewind in case something is not very clear. And I hope the board is yeah, it's quite clear. I hope everything is quite in focus. So I'm just going to pause there. Then I think we'll look at how Kali arrows and molecular orbitals, when they are going to be put together, how they can help illustrate a certain mechanism. Okay. I hope you are enjoying this course. Okay. Thank you.